So, welcome everybody to the first colloquium in analysis. So, today's speaker is Professor Virginie Ehrlacher from the Colloquium Virginie is an expert in the design and analysis of numerical methods for very high-dimensional problems. With a looking at goal of simulating complex systems arising, for instance, in material science, quantum chemistry, molecular dynamics, cloud motions, and many more. And so the model order reduction for such difficult problem requires to master quite a wide range of, let's say, tool of mathematics like PDE analysis, stochastic processes, tensor numerical methods, and also machine learning. And Virginie, for several outstanding contributions to this field, got awarded. She was awarded with the Lévy-Lieb award from the French Academy. She also got a ERC starting grant, so she is an amazing speaker for this colloquium. And in this talk, she will talk about certain link between optimal transport and functional density theory, which leads to such a sparse approximation problem. And yeah, I think that's it. So the stage is yours. Thank you.
Yeah. Thank you so much, Stefano, for the very nice introduction and for the invitation. It's a great pleasure to give this talk here in front of so many nice colleagues. So indeed, what I'm going to talk about today actually is based on a series of joint works with Aurélien Alfonsi, Raphaël Coyot, Damiano Lombardi, and Luca Nena. And these are, let's say, a collection of sparsity results on some quantum and classical optimal transport problems that arise from quantum chemistry applications. So the first part of my talk, sorry, I need to be a bit closer to the laptop. So the first part of my talk will be about the motivation of this work, which is mainly about electronic structure calculations for molecules. So I'll give you some introduction to the field for those of you who are not familiar with it. Okay. Then I'll switch to what's called density functional theory, which is a theoretical framework that is mainly used in order to do electronic structure calculations, and it's linked with optimal transport. And there's Giuseppe, which is one of the leading experts in the field, so I'm very happy to talk about this here. And lastly, I will talk about the sparsity results themselves, okay, which are based on moment-constrained approximation of this quantum and classical optimal transport problems. So please feel free to interrupt me anytime if you've got questions, if some things are not clear. Stop me anytime. Okay, so let's begin with the motivation, which is about electronic structure calculations for molecules. So for those of you who may not be familiar with quantum chemistry and so on, you can think of a molecule as being an assembly of nuclei, which are quite heavy particles, okay? They are composed of protons and neutrons. And at the scale, you can assume them to behave like classical particles. So the nuclei within the molecule, you can describe the state by their positions and their electrical charges, okay? And in addition to the nuclei, so sorry, for instance, here, this is a schematic picture of an H2O molecule for water, okay? And so here you see the oxygen nucleus and two hydrogen nuclei. Okay? And in addition to this nuclei, you've got the electrons that plays a role of a kind of gluing cloud around this nuclei that enables the molecule to remain stable, okay? But electrons are much lighter particles than nuclei, than protons and neutrons. And at the scale, you cannot model them as classical particles anymore. You have to model them as like quantum particles. And so we'll rely on quantum chemistry concepts in order to describe the state of the electrons within the molecule, given positions and charges of the nuclei. That's what we are after in this type of context. And more precisely, what we are after, and which is of vivid importance for quantum chemists, is to know what is the state of the electrons within a molecule that yields the lowest possible energy. So this is called the ground state of the electrons. And why is this important? It's because knowing this ground state of the set of electrons enables to predict many properties of the molecule, electric, magnetic, chemical reactions, and so on and so forth. And so that's what we are after here. Okay. So sorry. Oof. So the holy grail in this type of applications is the so-called many-body Schrödinger model. Okay. So here I'm going to consider a molecule that will be a physical system composed of some nuclei, okay, plus a system of n electrons. So as I told you, these n electrons, they must be modeled as quantum particles, and as a consequence, their state will be described by means of a so-called wave function, okay, which will be denoted by psi in the rest of the talk. And psi is a complex valued function, which is defined over R3n, where n is the number of electrons in the system. Okay. This wave function, and in addition, we are going to assume that these n electrons, they are subject to some external potential. This external potential may stem from the nuclei inside the molecule, or from other types of external interactions like lasers or things like this. And this external potential will be denoted by V, okay? And this will be a function defined on R3 with values in R plus infinity in general, okay? Okay? So just for those of you who are not familiar with quantum chemistry, the wave function that describes the state of the electrons within the molecule, it has the following interpretation, namely that the model square of the wave function evaluated at x1 up to xn, where x1 up to xn are vectors of R3, this represents the probability density on finding the n electrons at positions x1 up to xn respectively. Okay, and so this has the following consequence, which is that if you consider a subset B of R3n and you integrate the squared modulus of the wave function over the set B, this gives you the probability that the positions of the electrons are located in the set B. And so, in consequence, you also have got this normalization condition, which is that if you integrate the modulus square of the wave function of the whole space R3n, well, you get 1, because you've got the probability 1 of finding the electron somewhere in R3n. Okay. Okay. In the talk, we are going to consider a set of n electrons that have finite kinetic energy. And this will translate into some conditions on the set of admissible wave functions that can describe such a set of electrons which have finite kinetic energy. So the set of admissible wave functions throughout the talk, it will be denoted by an, okay, curly an. And then it will be the set of wave functions psi, which will then be a squared integrable over R3n with L2 non equal to 1. And such that the gradient of psi is also itself a square integrable function. Okay. And in addition, you require that psi has to be an anti-symmetric function. This is actually a consequence of the so-called Pauli principle, which states that you cannot find two electrons at the same location. This is not. This is to make a long story short. Okay. And in particular, this anti-symmetry properties, it writes in the following sense. If you consider sigma to be a permutation of the set 1, 2, up to n, and if you consider the evaluation of the wave function psi at points x sigma 1, x sigma of n, this has to be equal to the signature of the permutation sigma times the value of psi evaluated at x1 up to xn. Okay? And you can see from this, if you just, that the consequence of this is that if you evaluate the value of psi at n vectors and two of them are identical, necessarily the wave function has to be 0. So this is one way to mathematically encode this Pauli exclusion principle. All right? And so this is the set of admissible wave functions that I will be able to, that will describe the state of my n electrons. Okay? And I'm going to look for the ground state of the electrons within this admissible set. Okay? And how do we define it? Actually, for a given value of the external potential acting on the set of electrons, the ground state energy of my electrons will be given by this quantity here that will be denoted by Eg of V in the rest of the talk. And Eg of V is then the infimum value of the energy of the set of electrons that over all admissible wave function that describe the state of the n electrons in the system. Okay, so it's a solution of the following minimization problem. And here, the energy of a set of electrons described by wave function psi, it's given as a sum of three terms. Okay, this term here plays the role of the kinetic energy of the electrons. I'm going to write the expression like that. This quantity here, CEE of psi, will be related to the Coulombic interaction energy of electrons within themselves. And this quantity here will be related to the energy yielded by the external potential on the system of electrons. Okay? And all these terms are actually quadratic in psi. Okay? So for the kinetic energy, this is simply 1/2 times the integral of the square of the gradient of the wave function. The electron-electron interaction energy is equal to this quantity. This is the integral of a function c that is written here times the square modulus of psi. And here the function c is given as a sum of all Coulombic interaction potentials between all the different pairs of electrons located at points xi or xj. Okay. And lastly, the external potential energy writes under this form here. So here what you see, you still see an integral times the square modulus of psi, the wave function, times the sum of the values of the external potential evaluated at the positions of all the electrons in the system. Okay. And so all in all, if you want to identify what is the ground state energy of your system of electrons within the molecule, within the presence of this external potential, you have to find some psi in the admissible set of wave functions that minimizes this energy, that is the sum of these three terms. Okay. And so if you write the first order optimality conditions for this minimization problem, because of the normalization condition that I've introduced to you before, you end up with an eigenvalue problem. Okay. More precisely, a minimizing wave function, which will be denoted by psi g here, will be the solution of this eigenvalue problem, where Eg of v is the lowest eigenvalue of an operator h and v, which is called the Hamiltonian of the electronic system. And this Hamiltonian operator, well, it writes as a sum of three terms, which stem from the three different terms in the, which appear in the energy. Okay. So here you recognize the Laplacian operator that comes from the kinetic energy. There is also a multiplication operator by the C Coulombic potentials that comes from the interactions of electrons within with themselves. And here you see one last term where the external potential applies. Okay. And so in particular, this Hamiltonian operator, I can write it as a sum of two terms. One term where I externalize the influence of the external potential, and another term here, which is just the sum of the contributions of the Laplace operator and the electronic Coulombic potential. Okay? And the sum of these two terms will be denoted by Hn0 in the rest of the term. All right? So this seems simple in the sense that this guy is a linear eigenvalue problem. Big problem is that n is big, and if approximating numerically a function that is defined over a state of dimension R3n when n is several hundreds or so, well, it's more complicated. Okay, so because of that, because in practice one wants to deal with a large with a system with a large number of electrons, traditional numerical methods for this type of problems are prone to the curse of dimensionality. And you cannot use standard finite element methods to deal with this kind of eigenvalue problems. You have to do something else. Okay. And so quantum chemists have worked for years and years and years to find ways to deal with this curse of dimensionality. So today I'm going to talk about density functional theory that was introduced by Cohn and developed by Sham and collaborators. Okay. First, this theory, Walter Cohn was earned a 1998 chemistry Nobel Prize, so it was he had a huge impact on the field. Okay, and this density functional theory is a theoretical framework that enabled to yield another point of view in order to yield to some numerical approximations of this electronic Schrödinger problem I just presented to you, while trying to avoid the curse of dimensionality. And so that's what I'm going to tell you about in the next slide. Okay, for this I need to introduce some additional notation. Okay, so here for a given psi in my admissible set of wave functions an, okay, I can define an associated electronic density that will be denoted by rho psi, and this guy is a real valued function which will be defined on R3 instead of R3n, which is the definition domain of the wave function psi. Okay, so the electronic density rho psi will be defined on a much lower dimensional space. Okay, and more precisely, for any vector x in R3, rho psi of x will be defined as n times integral over all the vectors x2 up to xn, not the first one, of the squared modulus of psi, where you take the first variable to be equal to x. Okay, so this guy actually, you can view it as a probability density of finding one electron somewhere in the space, okay, out of the n. All right, and this will be a key quantity in the density functional theory I'm going to tell you about just now. Okay, there is one key result that make this theory very practical, which is the following, and this is the rigorous mathematical proof is due to Lévy and Lieb. Okay, and it consists in making the following observation, which is not trivial to prove. Okay, the following observation is the following one. If you consider the set of electronic densities that you can produce out of any admissible wave function, well, this set here, you can identify it as a set of non-negative functions defined over R3 that are integrable, and the integral of which is equal to n, the number of electrons. And such that the integral of R3 of the gradient of the square root of rho squared is a finite quantity. Okay, so you've got an explicit characterization of the set of all electronic densities associated to any admissible wave functions for your set of n electrons. This is particularly nice, and this set, in the following I'm going to denote it by in. Okay, this is particularly nice because then what you can reformulate the minimization problems that gives you the ground state energy of the set of electrons that I've introduced before. Okay, so remember, this guy was originally defined as the minimization of the energy of the set of electrons over the set of admissible wave function, okay, which are guys defined on R3n. And now this quantity, thanks to this Oerenberg theorem and thanks to this identity, you can also reformulate it as an alternative minimization problem, which is not defined on a set of wave functions, but only defined on a set of electronic densities that are only functions defined on R3 and not on R3n anymore, and so which are much lower dimensional objects. And so this is cool in principle, okay, in the sense that more precisely, the ground state energy of the set of electrons, you can prove that this is the minimum value over the set of all admissible electronic densities, that are these guys, okay, of some electronic density energy functional, that is a sum of two terms. Here you see there is a term where the external potential of the system appears, okay, which is explicit in terms of rho. And you've got another term which gathers the contributions of the two terms that are related to kinetic energy and electron-electron interaction energy, okay? And this guy here is called the Oerenberg functional. So it's a functional which depends on some electronic density rho belonging to this set in, okay? So this is cool on the paper, because then to identify this ground state energy of the set of electrons, one in principle should only solve these minimization problems defined on functions only defined on R3 and not on R3n anymore. Yeah, but life is not as simple as that, okay? Actually, the problem is that to identify this Hohenberg functional, you have to solve a problem that is at least as complicated as the original Schrödinger problem. Okay, so from this is disappointing, and somehow you may feel that okay, we have gained nothing. More precisely, this Hohenberg functional FHK of rho is then defined as the infimum over all admissible wave function, the electronic density of which is equal to rho of the sum of the kinetic energy and the electron-electron interaction energy. Okay, but that was the start of the development of a huge zoology of quantum chemistry models that have been used in practice by quantum chemists, nevertheless. Because even though this Hohenberg functional is not known explicitly, people have put lots of efforts in order to build approximations of it that then are amenable to practical calculations. And this gives rise to a huge zoology of different models. So this is just a bunch of names that appear in the quantum chemistry literature. So Conchamel DA, GGA, hybrid functional, blah, 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 blah. So, and all these models, well, most of them rely on some type of approximation for these Hohenberg functionals, often obtained in some asymptotic regime. Okay. But that's the way it is. And then here in this talk, I'm going to talk about approximations of these Hohenberg functionals and Giuseppe was a huge leader in the field that are linked to optimal transport theory. So this is one part. I'm going to talk about one particular way to see approximations of this functional. Well, more precisely, I'm going to talk about two different ways that are both related to optimal transport. Okay. And so the rest of my slides is about introducing these two types of approximations of these Hohenberg functionals that are related to optimal transport theory. Okay. Among many others that exist. Okay. I'm going to introduce a first approximation that was introduced by Lévy-Lieb, at least up to my knowledge, and which was built upon the observation that even if we knew exactly this Hohenberg functional, which we do not, okay, we would still run into problems to solve them. The minimization problems I just shown you here, because actually this guy is not convex. Okay, so a priori, even if we had access to this quantity, there would not be uniqueness of the minimizers of this guy, or even in practice, you might run into some problems in the sense that there may be some local minimizers to this quantity. Okay, and Lieb didn't like that, and he had good reason not to like that. Okay, and so that's why he introduced another functional, which is called the Lieb functional, and which has very nice properties that I'm going to tell you about. So this other functional, Lieb functional, I'm going to denote it by FL of rho in the rest of the talk. Okay, and this will be an approximation of this Hohenberg functional. Okay, more precisely, Lieb said, okay, I'm going to define this new Lieb functional as a convexification of the Hohenberg functional. And so this guy, there are several ways to have a look at it. The simplest way, the first way to consider it is to define it. So for a given electronic density, FL of rho will be given as the solution of the following minimization problem. Where here, what do you see? What are you minimizing? You're minimizing over a sequence of non-negative numbers alpha I, a sequence of potential electronic densities rho I, for I in a positive integer, of the sum of the I of alpha I times the Hohenberg functional evaluated at rho I, under the constraint that the sum of the I of alpha I rho I is equal to the original rho. Okay, so this gives some functional. This guy is named the Lieb functional, and in general, it does not coincide with the Hohenberg functional. It does not coincide with the Hohenberg functional, but you still have the very nice property because you really define the good object and so on, that the ground state energy of the electrons is still the solution of the following minimization problem, which is very similar to the one I've introduced before, except that here you replace the Weinberg-Kohn functional by this Lieb functional, which is its convexification. Okay? And that's a nice property, because it means that using this guy instead of the original guy doesn't change anything in terms of, in the principle, in terms of computing the ground state energy. Okay? Okay? And actually, this Lieb functional is linked to quantum optimal transport theory. And that's the aim of the next slide, to explain you the link between these two quantities. To explain you the link between quantum optimal transport and this Lieb functional, okay, I need to use introduce trace class operators. Okay. So more precisely, these guys will be some particular operators that will act onto a space of wave functions. So more precisely, here H0 of n is a set of wave functions that are in L2 and anti-symmetric. Here I don't consider the finite kinetic energy property I was requiring for the admissible set I introduced before. And here, sigma 1 plus, it will be the notation for the trace class operators I'm going to consider. More precisely, these guys, they will be the set of self-adjoint non-negative trace class operators that act onto this guy, H0n. Okay? More precisely again, this set of operators, okay, so they are the set of self-adjoint operators gamma that act onto this space, and that can be diagonalizable in the following sense. You can find a sequence of eigenvalues alpha I that are non-negative. Okay, sorry, I forgot. No, that's here, sorry. And the sum of which is finite. And you can consider psi I an associated orthonormal basis of H0n associated to each of these eigenvalues. Okay, so that for all I, you can find an orthonormal basis psi I of H0n such that gamma psi I is equal to alpha I psi I. Okay, and these alpha I are related to the alpha I before. Okay, okay, so that's just some notation to introduce the set of operators I want to consider here. And what happens is that to one such operator, you can also define an associated electronic density in the same way, in a similar way, that one could associate an electronic density to a given wave function. So the expression is given here, okay? Assume that you've got gamma, a trace, such an operator that has such an eigenvalue decomposition. Then the associated electronic density is defined as a sum from I equal 1 to plus infinity of alpha I eigenvalue of gamma times the electronic density associated to psi I, where psi I is an eigenvector of gamma associated to the eigenvalue alpha I. Okay. And so you see this formula enables to define electronic densities associated to operators out of the definition of electronic densities out of wave functions. Okay, and then what you can prove is that this Lieb functional, FL of rho, that was a convexification of the Weinberg-Kohn functional, you can also rewrite it as a solution of a minimization problems defined over the set of trace class operators gamma, the electronic density of which is equal to rho. And what you're minimizing is the trace of the operator Hn0, so this was the Hamiltonian of the system without the external potential, times gamma the operator. Okay. And this guy is actually a quantum optimal transport problem. So just I give you recall the expression of the Hn0 here. Okay. And actually, if you want to express this quantity in terms of the eigenvalues and eigenfunctions of gamma, you end up with this formula here. Okay, where T and CEE were the kinetic energy and the electron-electron interaction energy. Okay, and so that guy is a quantum optimal transport problem I'm going to consider later in the talk. Keep that in one corner of your mind. I'll go back to it later. Okay, So that was the first approximation of the Weinberg functional I wanted to tell you about. Yeah.
You need to ask anything to be finite in space of psi I.
Here, no, but actually, you see there is an int here. And here in the expression of the trace, Hn0 gamma, here there is the L2 norm of the psi I that will come into play. So for this quantity to be finite, actually, an output of it will be that the minimizer of this guy has to have its eigenfunctions to be a finite kinetic energy. But to have self-adjoint, well, to define properly the set of gamma, gamma has to act on the L2 functions. Okay. Thanks for the question. Are there other questions? Because before I go to the second approximation. Okay. So that's one approximation, which is a quantum optimal transport problem. Okay. Now, let me introduce the second approximation of the Weinberg problem. This second approximation was considered originally by these people who are quantum chemists, okay, and Giuseppe knows them very well. And actually, they wanted to build an approximation of the Weinberg functional by means of some semi-classical limit. So let me explain to you what they had in mind. More precisely, what they considered is the following quantity. So consider a parameter h which is positive, okay, which will play the role of a semi-classical parameter. And you can consider the following h-dependent Weinberg functional, okay, which is still a functional of an electronic density rho, and which is the solution of a following minimization problem. So here you see it is very, very close to the definition of the original Weinberg functional, except that in front of the kinetic energy term, you put this small h parameter. Okay. That's the structure of the problem is the same. And then these people, they had the idea to consider as an approximation of the original Weinberg functional, to consider the limit of this quantity, as h goes to 0. Somehow here the interpretation that they had was that they wanted to consider strongly correlated electrons, where the effect of interactions of electrons within themselves were much stronger than the effect of kinetic energy. And so that was the type of asymptotic limits they considered in order to define an approximation of the original Weinberg functional. Okay? And so actually, this guy here can be rigorously proved to yield a classical optimal transport problem. And this is the objective of my next slide. So just to give you an idea of where the optimal transport problem, classical optimal transport problem comes from, you can think of, you can make the following observation, which is if you consider an admissible wave function psi here, and consider its squared modulus, psi squared, from what I told you, well, gamma psi, this quantity, then defines the symmetric probability measures on the space R3n. Okay? And then the electronic interaction term, CEE of psi, you can also write it as the integral of the R3n of the Coulomb function C times these probability measures, gamma psi. All right? And then what these people prove, and also Giuseppe worked a lot on this type of problems, they prove that this semi-classical limit of the Weinberg functional I've introduced to you before, you can actually rigorously prove that it is also the solution of the following minimization problem, where you minimize only terms that are derived from these terms here. You minimize the integral of the Coulomb function C times gamma over the set of all gammas that are probability measures defined on R3n and that are symmetric, and such that an associated electronic density, rho gamma, is equal to rho. What is the associated electronic density associated to such a probability measure? This is given by this formula here, okay? So for a given symmetric probability measures gamma defined on R3n, rho gamma will be a probability measure defined on R3, that is defined by means of this formula, where you see gamma appearing here. Okay. So that in particular, if gamma stems from some wave function psi, you've got this relationship which holds. Okay. And another way to view this formula here is that actually rho gamma is up to the n multiplicative factor that you see here. It's a one variable marginal of the probability measure gamma. Okay. And so here, this guy, you can interpret it as a marginal constraint of a gamma given probability measure. And so what you're minimizing here is the integral of a cost function against measured gamma over symmetric probability measures gamma, the marginal of which is equal to rho. And this is indeed a classical optimal transport problem. And that's the second approximation that I want to talk about here. Okay, so just a brief recap. Now, for now, I've introduced you two approximations of the Weinberg confunctionals that are both related to optimal transport theory. The Lieb functional that reads like a quantum optimal transport, okay, and the SCE functional that reads like a classical optimal transport. Okay, and so this is two different approximations. Both can be interpreted in terms of quantum or classical optimal transport theory. Okay, and so what we've done is to try to to design some numerical methods in order to try to approximate these two quantities. Okay, so just to briefly tell you why this is a difficult problem. Here it's just explaining what happens, for instance, in the case of a classical optimal transport problem. If you approximate it with standard discretization grids, okay, you still face a curse of dimensionality, and the complexity of the problem scales exponentially with the number of electrons. So you haven't gained anything.
The usual number of electrons, the typical application.
So here I'm going to show results with 100 electrons. That's where we can go with this type of approaches for typical. So this is reasonable number of electrons, but you would like to go even beyond that. That's where we are with this type of optimal transport problems. But the higher you get, the better it is. Huh? Not with this type of approaches. But with this type of approaches, I've got to test with 100 electrons. You'll see in the variant. Okay, so there are lots of people who have considered different ways to try to circumvent this curse of dimensionality. Okay, so there are some methods that rely on the entropic regularization of optimal transport problems. So here there are mostly algorithms which dealt with the classical optimal transport problem. Okay, there are also approaches that that build on a method called genetic column generation algorithms. These were developed by collaborators of Gero Frieseke, mainly. And here, with Luca and all these people, well, what we tried was to yield an alternative point of view in order to build numerical approximations of these two quantities, quantum optimal transport, classical optimal transport, which try to avoid this curse of dimensionality and which relies on moment constraints. Okay. And what I'm going to tell you about now is about this approach that we studied. And the interest of this approach, well, one of the interests, all methods have pros and cons, is that it leads to some sparse minimizes. And this property can be used in order to implement numerical schemes. And so that's what the rest of my talk will be devoted to, about explaining to you what we can say about what are these moment constraints discretization and what we can do with it, basically. Okay. So here we go. So here, the approach is the following. So the previous approaches, they mainly consist, most of them, into discretizing the space on which either the probability measure, let's fix, for instance, the classical optimal transport problem to fix the idea. Most of the existing approaches, they rely on the introduction of discrete grids of the set where the probability measures are defined. So typically in introducing discrete grids of R3n and then trying to compute approximation of the probability measures as measures defined into this discrete grid of R3n. Here, we took an alternative point of view, okay, which was the following. We didn't want to discretize the space on which the probability measures were defined. Okay, so here I'm talking about the classical optimal transport problem just to begin with. Okay, I'll go to the quantum optimal transport problem later. And so we didn't want to discretize, to introduce a discrete grid. So we rather rely on moment constraint approximations. So let me explain that. Here, just for the sake of simplicity, this is an assumption that we can relax, but only complexify things for the sake of the talk. But for simplicity, here I'm going to assume that rho, the electronic density that appears in the Lieb or the SCE functional, I'm going to assume that it is compactly supported into some compact subset Q of R3. Okay. And then we are going to introduce some moment functions, and more precisely, we are going to introduce a sequence of moment functions that will be denoted by phi m for m a positive integer. These functions will be continuous functions defined on R3, okay? And we are going to require the following assumptions onto this set of moment functions. Well, first assumption, we need the function equal to 1 to belong to this sequence, okay? So let's take it as the first function, okay? First assumption. Second assumption, we need this sequence of functions to have some natural density properties. More precisely, we are going to require that for any function f that are continuously defined on the compact support Q, compact set Q, that you can approximate it arbitrarily close by some Fm functions that belongs to the span of the big M first elements of the sequence. Okay, so more precisely, we are going to require that you've got this natural L infinity density assumption onto the family of moment functions. Okay, and now for any M in N star, we are going to define rho M as being the moment of the electronic density rho associated to the moment function M, phi M. Okay, so rho M will be the integral of R3 of phi M times rho. Okay, and now what we do is that we replace the original quantum and classical optimal transport problems where you add these different constraints appearing. Remember, in the classical optimal transport problem, we had this quantity rho gamma, where gamma was a probability measure on R3n, which was imposed to be equal to some rho. It was the SE case. In the Lieb case, you had a similar constraint where here rho gamma was the electronic density associated to an operator. Okay. And here we replace these constraints, which are infinite dimensional constraints, either on gamma or the probability measure or gamma operators, by only a set of M scalar constraints that are given as a M moment constraints associated to the big M first element of the sequence of moment function. So instead of imposing these constraints, we relax them by only imposing that the integral over R3 of Im times rho gamma, or rho gamma here, is equal to this rho M quantity I just introduced. Okay? And so, of course, this set of M moment constraints are much less demanding than the full constraint of the original problems. Okay? And so, if you do that, you end up with relaxed optimization problems, okay, which depend on M, the number of moment constraints that you impose, both in the classical case or in the quantum optimal transport case. Okay? And this guy so yields approximations of the original SC functional or Lieb functional. Okay. In particular, in the classical case, this guy, you can view it as a particular instance of a generalized moment problem for those of you who know about this literature. Okay. So this gives some approximation of the original classical or quantum optimal transport problems, okay? And M here plays the role of a discretization parameter. All right? Then because of the density assumptions on the moment functions that I've just introduced to you, then you've got a safety check result, okay? Which tells that if you let the number of moment constraints go to infinity, well, both these approximations in the classical or in the quantum case, they both converge to the exact value of the functional that you're interested in. And just wanted to mention that there are links with other works related to Lieb functionals or of this SEC functional here. Okay, so that's, let's say, a safety check result. Okay. Now, what's really interesting about this approximation is that if you fix M, the number of moment constraints, then here I'm stating the result, the sparsity result in the classical optimal transport case. Then you can prove that there exist minimizers to the moment constraint approximation, gamma, that are given. So here in the classical optimal transport case, again, sorry. So these guys are probability measures defined on R3n, okay? And you can find minimizers that can be written as discrete measures, okay? That are some weights wk times Dirac masses located at some points xk in R3n, okay? And the sum of Dirac masses entering the decomposition of these minimizers, here's number k, you can prove that necessarily you can find some minimizers such that k is lower than m plus 1, where m is the number of moment constraints, okay? Why is this interesting? Because if you look at the complexity of such representation, actually this representation is very sparse in the sense that if you only have to identify such weights wk and such points xk, the complexity of representing wk and xk only scales like m times n the number of electrons. And you see here, if you fix the number of moment constraints, the complexity only scales linearly with the number of electrons, whereas with traditional discretization methods, this complexity scaled exponentially with the number of electrons. So this is a much, much sparser representation for the solution of these optimal transport problems. And that's what we want to exploit then in the numerical scheme. Okay, because then trying to identify weights and points in such a kind of representation will be much, much cheaper than discretizing, representing the probability measure on a fixed discrete grid. Okay. And you've got a similar sparsity result in the case of the quantum optimal transport problem. Okay. So here it writes as follows. Here I'm first introducing a notation, which is a bracket notation, sorry for that. This guy, for a given wave function psi, it is the orthogonal projector onto the space spanned by the wave function psi. Okay, this is an operator. And so what you can prove is that if you consider the moment constraint approximation of the quantum optimal transport problem, you can also find some sparse minimizers, which are operators in this case. And these operators can be written under the following form, where here you still see what plays the role of the Dirac masses in the classical case. Here are these orthogonal projectors. And you see here that you've got a sum of k terms, k being also lower than m plus 1, where m is the number of moment constraints that you have. Saying it differently, in this moment constraint approximation, you can find some minimizers that are operators with low rank, okay, and the rank of which scales linearly with m, the number of moment constraints that you have. And actually, both the sparsity results, they can be both obtained by the same type of results, which was the atomic bomb in the analysis, which is called the Chakalov theorem. Okay. So that was the sparsity results about minimizers of these moment constraint approximations. Now I'm both valid in the classical and quantum optimal transport case. Now I'm going to focus more specifically about this, the scheme that we developed in the classical optimal transport case, because easier to explain than in the quantum optimal transport case. Okay. So here in the classical optimal transport case, remember, we want to find a minimizer of this moment constraint optimal transport, classical optimal transport, under this form. Okay. And so natural idea is to say, okay, we are going to look at weights wk and positions xk, which minimizes the functional that that we have. Okay. And so if you write things, this boils down for a given number of weights and particles, wk, xk, to minimize such a quantity here. Okay. So that's really plugging the representation I gave you into the expression of the minimization problem I introduced before. Okay. And so, okay, now you're looking at weights wk and position xk that are solution of this minimization problem. Okay. So this is a very sparse optimization problem in the sense that the number of quantities that you have to identify only scale linearly with the number of electrons instead of scaling exponentially, which is again in the interest. But of course, there is no free lunch, okay? In the sense that now, this minimization problems, if you write it in terms of the weights wk and the points xk, well, this is not anymore a convex problem, which was the case of the original problem when it was expressed in terms of the probability measures. And so it's non-convex, and you've got non-convex constraints coming into play. So in order to deal with that, in order to find practically some approximation of this minimization problem, we relied on some stochastic gradient algorithm that actually can be written as constraint over d'Entlangement dynamics. And then we see what it gives. Okay. We've got no theoretical guarantee on the convergence of this practical stochastic algorithm, unfortunately. But well, we'll see what it gives. Okay. So here I'm going to show you some numerical results. First, some toy numerical results where the space dimension is 1, okay, and where you've got 5 electrons, okay. And we are going to consider 2 electronic densities. And this will be defined onto the interval -1, 1. So the first electronic density will be the uniform density, okay, and the second one will be given as this kind of oscillatory density, okay. So this is typically the value of the cost functional that you were trying to minimize along the iteration of the minimizing algorithm, so the stochastic gradient algorithm. And the different curves corresponds to different values of the number of moment constraints that we impose. And sorry, I forgot to mention that the moment constraints that we impose are Legendre polynomial test functions. Okay. And this is what we obtain. So why do we consider this 1D numerical results? It's because in this case, you can identify the analytic solution of the exact problems. So you can have a way to compare with analytic solutions to check whether the algorithm gives reasonable results or not. Okay. And here, remember, I've taken an example where we've got 5 electrons. So what you are after is a probability measure, which is defined on R5. Here, what is plotted is a particular 2-dimensional marginal for these probability measures. So in red lines, you see the support of the analytic solution of the exact probabilities distribution, again on a 2-dimensional marginal. Okay. And in blue here, what you see are the locations of the particles of the xk that are given as an output of the stochastic gradient algorithm. And what you see is that these particles tend to localize very close to the support of the analytic solution. Okay. And you see here the results obtained for different numbers of moment constraints. So this is, the case of, this is the case of the uniform density here. And you've got similar results in the case where you've got this bumpy electronic density. So at least on these test cases where you can compute the analytic solution, the stochastic gradient algorithm seems to give reasonable results in the sense that the sparse minimizes of the moment constraint problems that we consider, they tend to concentrate close to the support of the true exact solution. Okay? And just to give you some examples, so we also tried to run the stochastic gradient algorithm in a much higher dimensional context, where we do not have any analytic solutions to compare with, but we tried to see what it gave. So here, more precisely, we consider a system of 100 electrons. So in the space dimension, so we are in a 3D now. And we consider an electronic density, which is a sum of a combination of 6 quotient functions. And here we still consider polynomial test functions. And the number of moment constraints here is 52. That's the highest value we could go to. And so here, in this case, what you are after is a probability measures defined on the space R3 to R to the 300. Okay, so that's very high dimensional stuff. And here what is plotted are different two-dimensional marginals of this quantity. And what you see here are typically places where the particles that are obtained as an output of the stochastic gradient algorithm concentrate. Okay. So here we've got no clue. Well, we cannot guarantee that this is a reasonable approximation of the exact problem. Okay. We are trained now with Julien Rillier and Aurélien Alfonsi to prove convergence of the stochastic gradient algorithm. There might be hope in some cases, but there are some assumptions on the moment functions and so on, which actually are not exactly satisfied in this numerical test. But there is hope to have some kind of theoretical framework at some point, but this is still work in progress. Okay, and just here, I've presented you results for the classical optimal transport case. Okay, with Lucas, we also developed some similar types of algorithm based on the sparsity results I told you about for the quantum optimal transport case. So this type of numerical results, actually, we cannot go to very high dimension, and unlike the case of the classical optimal transport problem. So we are still thinking about it and trying to have some ideas. So just some conclusions about what I told you about. Here I told you about some alternative way to discretize this optimal transport that stems from quantum chemistry applications, both classical optimal transport and quantum optimal transport, by means of moment constraints, instead of discretizing this space on which the quantities are defined, to make things quick. And we considered some numerical stochastic gradient, constraint stochastic gradient algorithm in order to try to solve the minimization problems that we obtain using the sparsity results I've presented to you. So again, as I told you, there is we are currently trying to prove some convergence and some assumptions of the stochastic constraint gradient schemes that we use to solve the optimization problem. So we've got some hopes to get some results, at least on some assumptions on this on the classical case. Okay, that is still work in progress. In the quantum optimal transport case, you could design the same type of algorithm, but instead of having some stochastic particle scheme, you would have some stochastic partial differential equations to consider. So in the quantum case, we had this algorithm with Lucan, and I didn't tell you about for the sake of time. And here also, what we are trying to do is to design some numerical schemes that would allow for a larger number of moment functions. Because here, for the moment, we are stuck with a number in practice with a number of moment functions that scales like a few dozens, so 52 in the high dimensional case I told you about. So here, what would be better would be to increase slowly the number of moment functions and choose them more wisely. Okay, and that's all for me. Thank you for your attention.
Thank you for the very nice talk. Do we have questions? Yes.
Thank you, Virginie, for the very clear presentation. So my question is about existence versus non-existence of a solution. Indeed, it is known that when the positive charge of the nuclei is strong enough, you have a solution.
Yeah.
While if the positive charge is weak, rather weak, you don't have a solution.
Yeah.
And the so-called ionization occurs, which means some electrons escape to infinity. Now, in your simplified assumptions, you have the assumption that everything happens in a given compact set.
Yeah.
And this kills, of course, ionization.
Yeah.
So, my question is if in the numerical simulation, you can see the ionization by seeing some parts of the electrons on the boundary of the box Q.
Yeah. So here, for instance, indeed, in the so I didn't show them, but Raphael did some numerical tests onto in a higher dimension where the support was a unit ball, and here you could see some boundary layer effect in this. Absolutely. So, however, if you don't have this compact support assumption that I've taken for simplicity, you can derive, you can show that you can have compactness, but up to the price of making additional assumptions on the electronic density rho. So to make things simple, you need rho to be decay sufficiently fast at infinity. Okay, and you need also rho to be uniquely defined out of its moments, which may not be always the case for any electronic density. But up to this type of assumptions, then you can recover some compactness result.
But it is very interesting because the threshold between existence and non-existence is not known.
Yeah.
And so maybe by numerics, if you can see the boundary concentration, you can estimate this threshold.
Yeah, probably. Yeah, it's a very, very nice remark. We didn't think about that, but you're perfectly right. Yeah.
Other questions? Yes.
I'm not very familiar with the stochastic gradient, but what is the main cost there?
Okay.
So how you have to evaluate the function, suppose, and evaluate the gradient somehow.
Yeah. So here mainly the cost here. So basically it tries like a particle scheme, interacting particle schemes. So you've got these k particles arriving, and you've got a driving force, which is the gradient of the c cost that I've introduced to you. So if you compute the gradient, you've got basically n minus 1 terms, okay? And so basically the cost is like n squared, to roughly. So it's still lower than exponential, so that's why we can do that. Actually, we didn't use any advanced tricks there, because in practice, people who would run these interacting particle schemes, they would have some hierarchical tree to detect where are the particles that are close to one another, and kind of neglect effects of particles that are far from each other. Okay, but this we didn't. Okay, and so you end up with some n square like cost for each time step. Yeah.
So this is the results you were showing us were run on the laptop.
Not exactly. Well, it depends on which one. So the 1D, yes, were run on a laptop. But this guy, the last guy, you needed to run it on a cluster. So it was not a very optimized cluster. It was the cluster of our lab, which is a bit old now. But you had to parallelize some step. So I think there were 32 nodes, something like this, to parallelize.
Other questions or remarks? And curiosity, if you go back to slide 9, so where you have the eigenvalue problem description.
Yeah.
So yeah, and so if you imagine you discretize this, so you get an eigenvalue problem with matrices of an insane dimension. Because I've seen this paper on Aula some years ago where they have, I think the same problem, maybe a slightly different operator, but they have the kinetic part, the potential. So these matrices are kind of sparse, you know how to apply them to vectors, for instance. And they were doing like simple mechanism like a power method or inverse power method because we want the minimal eigenvalue, let's say. And they were hardly thresholding. So they started with a very sparse eigenvector and then the threshold. With also some randomized rounding. So you round the probability that depends on the magnitude of your approximation of the eigenvector. And they were claiming that in some probabilistic sense, so this eigenvector converged to the true eigenvector, and it was claimed like that they were able to treat on plus or something. So matrices that are of dimension of like the Aula number, like the kind of things. Yeah. So I was wondering whether you have seen these kind of approaches also for your problem, whether they provide some meaningful results in your experience. Maybe, of course, at the end of the day, you don't have the true eigenvector to be sparse, but if you test it in the outer product or the real quotient, it may tells you some information about the quantity of interest. So, have you ever seen something like this?
So I've seen things close to close to thresholding and so on, mainly for the density functional theory approximation models. Because then actually this problem here is replaced by an eigenvalue problem which stem from the density functional theory approximation that I didn't tell you about, okay? And here what you obtain are nonlinear eigenvalue problems where you've got a potential which depends on the electronic density, and you're computing molecular orbitals that are defined on R3 and not R3. So I've seen some results like this, okay, for this mean field density functional theory model, where we function defined on R3. That being said, it would be interesting to see what it gives in this particular case. Here,
I'm sure that you have the potential magnetic terms. I'm not 100% sure about the electron electric interaction.
Yep.
It doesn't look sparse.
It's yeah. Well, directly on this, I haven't seen. What I saw were about this density functional theory approximation, where you compute molecular orbitals defined on R3, and you need to compute several eigenvectors, and you've got a mean field Hamiltonian that acts on functions of R3. And I'm not sure this is exactly the paper that you have in mind, but just related to this kind of thresholding ideas. There were some works by Reinhold Schneider, for instance, and Markus Parmeyer. So it may not be exactly the same, but. Okay. But I'm interested to see if you can. Yeah. Thank you.
Thank you. Other question? But not it's time for the coffee break. Let's thank the speaker again.